Hey everyone, welcome back to Calculus 3. This will be lecture 10 of the course. In this section, in the previous section, we talked about vector valued functions in the context of velocity and acceleration. In this section, we're going to extend some of our understanding of vector valued functions and the relation between the vector valued function itself and its derivative through the exploration of tangent vectors and normal vectors with respect to vector valued functions. So let's go ahead and jump into it. And so this will be section 2.4, again, tangent vectors and normal vectors. Okay, so previously we saw that velocity tends to point in the direction of motion. I'll write it. Points in the direction of motion. Okay, and this kind of a idea, right? So that's an idea out of physics, right? Specifically. But this idea can be generalized to basically any smooth curve, and not just a curve parameterized by time. So this can be generalized, okay, to any smooth curve. And that's kind of what we mean by a tangent vector. Okay, so let's go ahead and jump into that. So we'll have a definition here. Okay, we'll start with this definition. So let C be a smooth curve represented by R on an open interval I. Okay, so the unit tangent vector, and it's denoted with usually by T, standing obviously for tangent. So the unit tangent vector at T is defined to be, okay, how would we calculate it? Well, it's obviously T of T is equal to, now you take the position vector and you take the vector valued function of interest, position vector if we're talking about physics. You differentiate it. Okay, you take the derivative of the vector valued function and divide by the norm, okay, of T, or the norm of R, okay, where obviously R of T is non-zero. Can't divide by 0. So that's the definition of the unit tangent vector of a function. Okay, so let's do an example. Let's take a look at what we mean here with an example. We'll leave this on here. Okay, so we want to find the unit tangent vector. Let's find the unit tangent vector to the curve given by and we'll let our vector valued function be R of T equals T times I plus T squared times J. Okay, and specifically we're interested in the unit tangent vector when T is equal to 1. Okay. All right, so again, we're looking for this guy here, so we're going to need the derivative. So we'll first start by calculating the derivative. And that's just a simple matter. Okay, and you're going to get I plus 2tj. Okay. All right, then we'll say the unit tangent vector is going to be that guy, I plus 2tj, divided by the norm of R. And the norm of r is just going to be 1 plus 2t. Okay, so it's I plus 2t j divided by, and it's just going to be 1 squared plus 2t squared divided by, or the square root of that. And so we get, I guess we could say it's 1 over 1 plus 4t squared, and then the vector is I plus 2tj. Okay. All right. Okay, so that is the tangent vector in general. Now we want to know specifically what the tangent vector is, the unit tangent vector is when t is equal to 1. So then when t equals 1, what do we get? Well, we got t of 1 here, obviously, and that's going to be 1 divided by 1 plus 4 times 1. That's squared. We'll put that on there just for completeness. And then it's I plus 2 times 1 times j. Okay, and so this down here is 1 over the square root of 5. And then this is I plus 2j. Okay. And so maybe possibly a better way to write it would be to write 1 over the square root of 5 times I plus 2 over the square root of 5 times j. And this is approximately 0.447 and 0.894, approximately. Right, you can obviously see that's a unit vector, right? You can imagine squaring both of those components, adding them together. You're going to get 1, and away you go. Okay, so this is the unit tangent vector when t is equal to 1, right? So this vector, so this is t of 1. So this vector is specifically, what is this? Well, this is a unit vector that points in the direction of the curve that was given, okay, at t equals 1. Let's write that down, because how we interpret these things is kind of like everything here. Okay, so the vector, all right, let's rewrite this here. 1 times the square root of 1 over the square root of 5i plus 2 over the square root of 5j. This is a unit vector that points in the direction of the curve at, well, in the direction of the curve, and then we'll write the curve here. Just the curve was ti plus t squared j. So this is a unit vector that points in the direction of the curve at t equals 1. Okay, now what does it mean to point in the direction of the curve? Well, let's draw a picture here. Okay, let's say I've got my xy coordinates. We're in 2D space here. Okay, and so here I've got some curve. All right, and let's just say that this is t equals 1. Well, assuming that the vector valued function has a left to right orientation, then the direction of the curve here would be something like that, right? And if this is t equals 2, the direction of the curve would be something like that, right? And so on. Right, so you can probably get the idea. Right? Right, so this is basically has all the characteristics of what we would think of as a tangent vector. Okay. Technically, it's a vector, though, right? So it's not a tangent line; it's a vector, right? But it points in the direction of the curve for any specified t value. Now, the tangent line to a curve at a point t is specifically going to be the line passing through the point that is parallel to the unit tangent vector. Okay, so I mean there's a subtle difference there, right? So the unit tangent vector is a vector that points in the direction of the curve for whatever specified value of t. The tangent line to a curve at a particular point t is going to be the line that passes through that point that is parallel to the unit tangent vector, right? So some of this terminology just has to be kind of made plain. Okay, so there's a difference between a unit tangent vector and the tangent line to a curve at a point. Okay, let's look at an example. Okay, so let's find t of t, right, the unit tangent vector, and then find a set of parametric equations for the tangent line to the helix, and this is a specific curve called helix, to the helix given by, and here's the vector valued function. It is 2 cos t times I plus 2 sine tj plus tk. Okay. All right. And specifically at the point t equals pi over 4. All right. So what do we got here? Well, all right. So I'm going to attempt to draw something, and just to create context, right? This isn't going to be a specific drawing that we'll need much, but a helix in 3D space is kind of like a spiral. Looks a bit like this. Not exactly, obviously, but and this vector valued function is the equation describing this helix. Okay, so what we want, for some specific point on the helix, we want to graph. We want the parametric equations which describe the line that is tangent to the helix at the specified point, right? T equals pi over 4. Okay. So what we need to do is we need to first of all find the unit tangent vector, and then use that somehow to derive these parametric equations. Okay. So we're going to find the unit tangent vector, and so in order to do that, we're going to need the derivative of the function, right? So we need r prime of t. Okay, and that's just the derivative of this. I'll just write it just to be clear what we're doing. And we'll do it like this. This is definitely more detail than is necessary, right? But that's okay. So this will be negative 2 sine of t times I plus 2 cos t times j plus k. Okay, so that's our derivative. Next we'll need the norm of the derivative function. Okay, and so that's going to be basically square that plus square that plus square that. So it'll be 4 sine squared t plus 4 cos squared t plus 1. Right? Okay. And so this is nice because this is equal to 4 times sine squared t plus cos squared t plus 1. Right? And that, of course, is 1. So this is the square root of 4 plus 1, which is the square root of 5. Okay. And so then we can get to the unit tangent vector by dividing the derivative by its norm. Okay, so the derivative was negative 2 sine of t times I plus 2 cos t times j plus k, all divided by the square root of 5. Okay. And let's flip the page here. So basically we have this now. It's 1 over the square root of 5 times, let's see here, negative 2 sine of t times I plus 2 cos t times j plus k. Okay, so that's what the unit tangent vector is. And now specifically, what is the vector that is in the direction, what is the unit tangent vector that is in the direction of the curve at t equals pi of 4? So specifically, at t equals pi over 4, what do we get? Well, we can just evaluate that function, right? So t of pi over 4 would be 1 over the square root of 5 times negative 2 sine of pi over 4 times I plus 2 cos pi over 4 times j plus k. And let's see, what do we get here? So that would be, what is sine of pi over 4? That's square root of 2 over 2. So this is negative 2 times the square root of 2 over 2 times I plus 2, and then this is also square root of 2 over 2 times j plus k. And so 1 over the square root of 5 times negative square root of 2i plus square root of 2j plus k. Okay, and so that is the unit tangent vector at t equals pi over 4. So this is a vector that points in the direction of the curve at this specific value of t. Okay, so all right, so let's write down, what is this thing? This is a unit vector. We know that. This is a unit vector that points in the direction of the curve at t equals pi over 4. Okay, so we can use this vector here specifically to derive the parametric equations for the line that goes through whatever specified point. Okay, and so the direction numbers in particular can come off of this. Okay, so the direction numbers, are, and we can just pull them right out of there. So it's a equals negative square root of 2, b equals square root of 2, and c equals 1. Right, so we can just pull those right off the ijk piece. Right, the 1 over square root of 5 is common to all of them, so we can just exclude that piece. Okay. Okay, and so we know that this is the direction, these are the direction vectors, and that the point passes through, the line passes through, let's see, hold on one sec, what did it say? Okay, the tangent line passes through the point. I guess we have to plug it in, don't we? We'd have to plug it in to the original. Not a problem. It'll be 2 cos pi over 4i plus 2 sine pi over 4j plus pi over 4k. And what do we get there? 2 times the square root of 2 over 2i plus 2 times the square root of 2 over 2j plus pi over 4k. Okay, and so thinking of this as a point in space, well, or as a vector, I guess, you could think of it as the square root of 2 comma square root of 2 comma pi over 4, right? So whatever line, the tangent line here is going to have to go through the point square root of 2 better switch to the proper notation here. It's going to go through that point, isn't it? So the tangent line goes through the point, okay, and is in the direction of right, is in the direction of this guy, which we found up above. Okay, let's consolidate that information quickly. Let's consolidate all of that. So the tangent line at t equals pi over 4 is, so 1, in the direction of this guy. And we wrote this out, so it's 1 over the square root of 5, and then it's negative square root of 2i plus square root of 2j plus k. Okay, it's in the direction of this vector, and 2 goes through it's going to go through r of pi over 4, which we found to be square root of 2, square root of 2, comma, pi over 4. Okay, it's going to go through that point. Right, so then it's just a simple case to get the parametric equations, right? So remember the form, right? The form, the parametric equations can be derived using the form. Okay, so it'll be x equals, y equals, and then z equals, and it'll be what? x1 plus a times s, y1 plus b times s, and then z1 plus c times s, where a, b, and c are direction numbers, right? Yeah, we can plug these in, right? x1, y1, z1, that's just this guy. And pi over 4. And then that'll be, and then your a, we're going to pull off of this, a, b, c. So it'll be plus negative square root of 2s, and then plus square root of 2s, and then this one is just plus, basically 1s. Okay. All right, and so to summarize, so the tangent line is given by x equals square root of 2 minus square root of 2s, y equals square root of 2 plus square root of 2s, and z equals pi over 4 plus s. There it is. Okay, and so that gets us exactly what we needed, right? And this is specific to t equals pi over 4, obviously. Okay. All right. Okay. Okay, so that is the unit tangent vector. Okay, lots of other things you can do with this, but that's kind of an intro to it. Now, it's natural when you talk about the tangent vector to want to talk about vectors that are orthogonal to it, right? Because if the unit tangent vector is in the direction of the curve, we may want to know what is orthogonal to the curve, right, at any given point. And so there's going to be infinitely many vectors that are orthogonal to the unit tangent vector, right? Infinitely many, right? One of these is special. Okay, so there are infinitely many orthogonal vectors to the unit tangent vector. Okay, one of these, for example, is the derivative. right? So t prime of t is obviously going to be orthogonal to the unit tangent vector, right? And we know this, of course, because if you take the unit tangent vector and you dot it with its derivative, you get 0, which is a condition needed for orthogonality. Right? And we know also that t is a unit vector. T is a unit vector. How do we know that? Well, we kind of built it that way, but specifically that means that if we dot it with itself, we get the norm squared, which is 1, right, in the case of a unit vector. Okay, and so kind of taking these two facts here together, we can get to what's to a special vector called the principal unit normal vector. Okay, so let's define that guy. So we've got the unit tangent vector, and then there's infinitely many normal vectors relative to that vector, but there's one that's kind of special. We call it the principal unit normal vector. Let's define it. So we'll let C be a smooth curve represented by R, okay, on an open interval I. Okay. Now, if the derivative of the unit normal vector is non-zero, then and here's the name, principal unit normal vector. Okay, the principal unit normal vector at t is defined to be, okay, and so we usually use a big N for this because it's the principal normal vector, right? So it's just going to be equal to the derivative of the unit tangent vector divided by its norm. So kind of like how we got to the unit tangent vector by dividing the derivative of the vector valued function by its norm, we get to the normal principal unit normal vector by dividing the derivative of the unit tangent vector by its norm. Okay? And so that's that. Okay. And so let's do an example here. And these can be a little bit hairy because, well, it depends obviously on the function you're starting with, but these can get a little bit complex because of the differentiation, and sometimes these vectors can get a little bit more, they can get a little complex, I'll just put it that way. Okay, so let's do an example here. Let's find n of t and the unit normal vector at t equals 1. So we'll find the form of the thing, and then we'll evaluate it at 1 for the curve represented by this guy. R of t equals 3t times I plus 2t squared times j. Okay, so first, in order to find the principal unit normal vector, what we need is, we're going to need the unit tangent vector, right? So need to find t of t first. Okay, and so let's remember what t of t was. Right, it's going to be equal to the derivative over the norm of the derivative. Okay, it's basically the derivative. Okay, so we need r prime. And that's very simple here, right? Because it's just 3 plus 4t. 3i plus 4tj. Okay. And the norm there is just going to be, what, 3 squared plus 4t squared, the square root of that. And so we get 9 plus 16t squared. Okay. Okay, so we've got these two pieces here. And so a lot of times what can make this complicated, right, specifically getting to this principal unit normal vector, is the fact that you're normalizing, right? And so here, for example, this adds a lot of complexity to the vector when you have this kind of unpleasant factor on the front end of whatever vector you're talking about. And so that's what's going to kind of make this challenging, this calculation. But we're going to slog through it just as an example. Okay, so we know r prime and we know the norm. So then t of t, that's just going to be equal to, again, writing it, r prime of t over its norm. Okay, which in this case is 3i plus 4tj divided by, and here's the 9 plus 16t squared. Okay, so we got this guy. Okay. So now what we want to do, so next we want to get to this, don't we? Right? And we know that that is t prime divided by its norm. Okay, so we need to differentiate this first of all, and then we got to find the norm of that. Okay, and so t prime of t, right? Now you should think of this as a product. Really, this is going to be 1 over this, well, hang on one second. We should think of this as a product, so this is going to be the derivative of 1 over the square root of 9 plus 16t squared times 3i plus 4tj. Okay. All right, so we have to differentiate this. Now you can think of this as a product. It's probably the best way to think about it. Okay, so this is a vector valued function times a real valued function. Okay, and so what we have to end up using here is the product rule. Okay, so it's the derivative of, so it's the first times the derivative of the second plus the derivative of the first times the second. Okay, and so this will get a little convoluted, but let's go ahead and write it all out. We can do this. 9 plus 16t squared, and then we need to differentiate the vector piece. Okay, and then plus, now we have to differentiate the upfront piece here. And multiply that times the vector piece. Like so. All right. And then it's just a matter of go through and deal with the derivatives. And so this is 1 over the square root of 9 plus 16t squared. And then what happens here when we differentiate with respect to t? Well, everything kind of drops out except the 4j, right? So this is just 4 times j. Then over here, this is a derivative. Oh, sorry, there should be a square root there. Sorry about that. So this would be like, we'd have to use the chain rule. You can think of this as 9 plus 16t squared all to the negative 1/2 power. Okay, and so that would give us negative 1/2 times 9 plus 16t squared to the negative 3/2 power. And then we got to differentiate the insides like the chain rule. So this would be 32t, right, when you differentiate what's inside. And then all of that times this guy. Okay. Very good. And let's go ahead and clean this up a little bit. So we get 9 plus 16t squared up front. And we'll just leave the 4j next to it. And then I'm going to write minus. And the 32 and the negative 1/2 will cancel, and we'll just have a 16t up top. And I'm going to bring this all down into the denominator. 9 plus 16t squared, and then it's the 3/2 power. All times this 3i plus 4tj. Okay, so that is the basic. Basically, we've got all the derivatives worked out. Now we just need to kind of consolidate some of this and kind of clean this up. Now, this is totally my preference, but I'm going to switch over to component notation at this point, just because some of the simplification is easier, I think, if it's done that way. Okay, and so this here is equal to, now I'm going to put it in component notation. So what are my I terms? Well, I've got, let's see here. Yeah, so in this piece here, I've got 0i, right? So that's just going to be 0, and then the rest of it's all j. So it'll be 4 divided by this 9 plus 16t squared piece. Okay, and then I'm going to subtract from that this section over this vector over here. And this vector has an I component. And so it's going to be 3 times 16t divided by this 9 plus 16t squared to the 3/2 power. And then the j component is going to be the 4t times 16t divided by the same. All right, so 9 plus 16t squared to the 3/2 power. Okay, so this vector here can be written like this. This vector over here can be written like this. Okay, now I'm just going to combine them. We're ultimately trying to get down to one vector here. So when I combine everything, so this is basically 0 minus this piece. And so I get negative 48t divided by the 9 plus 16. And I'm going to rewrite that slightly. I'm going to write it as 9 plus 16t squared, the square root, and then the 3rd power. Okay, so that's the I component. And for the j component, it's going to be this minus this, so it gets a little bit crazy, but let's just write it out first. Okay, so it would just be that thing minus this guy here. And so this is going to be 64t squared. And let's see, that's going to be, well, it'll be the same, won't it? That should be to the 3rd power. Okay, so it looks like that. Oh, sorry, that one's not raised to the 3rd power, actually. That one's just squared. This one is raised to the 3rd power. Okay, so we have to get a common denominator here, won't we? Okay, no problem. All right, and moving on here, let's rewrite that. Okay, so we got square root and then the 3rd power, and then this next one is 4 over the square root of 9 plus 16t squared minus 64t squared over, sorry, 9, this will be the square root of 9 plus 16t squared cubed, right? So it's that. Okay, now this seems very complicated. It's just a little bit of an algebraic mess, right? And it's just because we were normalizing each of these vectors at each step. So what we'd want to do next is get a common denominator and combine these two terms. And so we can do that. And so that's just going to be 4 times, and we got to take basically 2 of these up here, right? So we'll have to have this term squared. So 9 plus 16t squared, that's the square root, and we got to square it. And then it's minus 64t squared all over this thing cubed. All right. And at this point, we can pull this out of the denominator, and that kind of makes our lives a lot easier. So 1 over 9 plus 16t squared square root cubed, and then the vector is just negative 48t, and then this is going to be this whole thing here. So this is the square root squared, so this will be just 4 times 9 plus 16t squared minus 64t squared. This one looks like that. No problem. And finally, we're getting pretty close here. We'll have to expand this. So it's the square root of 9 plus 16t squared, all cubed, and negative 48t. Now what can we do here? Well, we can expand all of this basically, right? And so what do we get? 9 times 4 is 36, plus, and it'll be 64t squared, and then minus 64t squared. Okay, so those two will drop out, and we're very close now. 1 over square root of 9 plus 16t squared, quantity cubed, and then it's negative 48t, apologies, negative 48t, comma, 36. Okay. And we see a common factor here, so I guess we could do this. Instead of 1, we'll make it a 12. And then that's going to give us a negative 4t, comma, 3. Okay? And so, what do we have here? So this is the derivative of the unit tangent vector. So the derivative of the unit tangent vector is 12 over 9 plus 16t squared to the 3/2 power times negative 4t, comma, 3. Okay, so that is our derivative. Now what's the norm of this thing? Because remember, the principal unit normal vector is going to be this divided by the norm of this. Right? So we still need that norm. Well, that's not going to be as big of a deal as the previous calculation. We're basically going to take, you can think of it like this, it's going to be 12 times negative 4t divided by 9 plus 16t squared to the 3/2 power, square it, plus 12 times 3 over 9 plus 16t squared to the 3/2 power, square it, and then take the square root. All right, and so we have a common denominator, so we can kind of combine these things. And so what do we get here? This is going to be 12 squared plus, well, sorry, 12 squared times negative 4t squared plus another, let's see, 12 squared. Okay. It looks like this. All right, so we can pull the 12 out, and what do we have here? Negative 4t squared plus 3 squared. Okay, so it looks like that. And let's switch pages here. Okay, so we've got 12 squared, and then we've got 16t squared plus 9 over 9 plus 16t squared to the 3/2 power, and then the square root of all that. And so this simplifies down pretty nicely, doesn't it? Pull the 12 out, and what do we have here? We're going to have 9 plus 16t squared on the top, and 9 plus 16t squared to the 3/2 power on the bottom. All right, and so this will cancel, won't it? Yeah, so we'll get a, let's see here. Well, one way to write it would be like this. We could write this as 12 times the square root of 9 plus 16t squared divided by, and I'm going to write it slightly differently. I'm going to write it like this: 9 plus 16t squared, and then that's the 3/2 power, and then squared again. Okay, and what's the advantage of that? Well, the squares cancel, right? And so this becomes 12 over the square root of 9 plus 16t squared over 9 plus 16t squared cubed. All right, and let's see, that is just 12 times the square root of 1 over 9 plus 16t squared squared. And I think the best way to write that is to take the square root of, well, you got the square root of something squared, so this is just 12 over 9 plus 16t squared. So it wasn't clear that it was going to simplify that dramatically, but it does. Okay, so then n of t, what is that one going to be equal to? Well, that is t prime of t divided by its norm, which we just found. Okay, so this is going to be 12 divided by 9 plus 16t squared to the 3/2 power times negative 4ti plus 3j, kind of pulling that from previous work, and then divided by the norm that we just found, which is 12 over 9 plus 16t squared. Okay, and this one will simplify very quickly. All right, so we'll just take this piece here, invert and multiply. So 9 plus 16t squared over 12 times this. Okay, and then negative 4ti plus 3j. Okay, and so here you get the cancellation. And what are you left with? Well, you're left with 1 over just the square root of 9 plus 16t squared times this vector. There it is. And so this is the principal unit normal vector. So there's nt. Now we need to know when nt is equal to, we want to know what this is equal to when t is equal to 1. So n of 1 will be basically 1 over 9 plus 16, square root of that, times negative 4i plus 3j. And this is 1 over the square root of 25, so it's 1/5 negative 4i plus 3j. So that's n1. Okay, very good. All right. So that's the unit, the principal unit normal vector, and that's how you would. That's an example of how the calculation might go. Again, finding that vector is not always trivially easy. I mean, it's relatively trivial. It's just that the algebra involved can become convoluted due to the normalization piece, right? So whenever you take that, whenever you normalize something, you have to divide by the square root of the sum of the components, and that piece can kind of turn it into a little bit of an algebraic mess, but it's a straightforward operation. You just got to be able to slog through that algebra. Okay, so let's kind of put this into context with what we talked about last time. So last time we talked about if you have an object traveling, like at a constant speed and velocity. Well, if you have an object traveling at a constant speed. So if you have an object traveling at a constant speed, we'll say, right? Meaning its velocity might be changing, i.e. in direction, but its speed, the magnitude of the velocity, is constant. Okay, we saw previously that when you have that situation, the velocity and the acceleration vector are going to be perpendicular to one another, right? So this implies velocity and acceleration are perpendicular, right? So we saw that like in the case of, for example, the example we did last time was of a circle, right, where the velocity was always changing, but the speed, the magnitude of the velocity was constant. And what we saw last in that example was that the acceleration is towards the center of the circle, the velocity is always perpendicular to that. Okay. Now, in general, so this is the case for objects traveling at a constant speed. Only for objects traveling at a constant speed. This is true only for objects traveling at a constant speed, right, where you have acceleration and velocity orthogonal to one another. Now, in general, this isn't true for objects that travel at a variable speed, right? This is not true when objects travel at a variable speed, right? I.e., the object is speeding up and slowing down and speeding up and slowing down, right? In general, part of the acceleration is going to act in the line of motion, and part of the acceleration is going to act perpendicular to the line of motion. Okay, so if this was a variable, if our object had a speed that varied, then at times you would have the acceleration be perhaps totally orthogonal to the velocity, but at other times, perhaps, a part of the acceleration would be towards the center, but then also a part of the acceleration would be in the direction of the velocity. And in this instance, what I've drawn here, the particle would be accelerating upward, or increasing in speed, right? And then maybe at other times, you would have the acceleration towards the center again, but then perhaps some portion of it in the opposite direction of the velocity, right? And in this case, you would see a deceleration, right? So velocity would decrease here, and velocity would increase in this scenario, right? So the takeaway here is that if an object's velocity is changing, then some piece of the acceleration, maybe not all of it, is going to be acting in the direction of the velocity, or in the case of deceleration, perhaps against the direction of the velocity. Okay, and so this unit tangent vector and this principal unit normal vector are going to be used as the components of acceleration to help you understand which piece is in the direction of the velocity and which piece is in, orthogonal to the direction of the velocity. Okay, so t of t and n of t will help us determine the two components of acceleration. Okay, all right, so let's talk that through. And that's a relatively straightforward exercise, right, once we have all of the machinery like this. Okay, so here's a theorem, and we'll prove this theorem. So if r of t is the position vector for a smooth curve C, okay, and n of t exists, then the acceleration vector a of t lies in the plane determined by, right, and determined specifically by t of t, the unit tangent vector, and the unit normal vector, the principal unit normal vector n. Okay? So if r is the position vector, and assuming that there is a normal vector, right, the acceleration could be 100% in the direction of the velocity, that's fine. So assuming that the unit normal vector exists, then the acceleration vector is going to lie in the plane determined by these two guys, right, the tangent vector and the normal vector. Okay, and specifically what that means is we're going to be able to write the acceleration vector as a linear a combination of these two vectors. Okay, and so let's prove this quick. It's relatively easy to prove. All right, so we're going to simplify the notation a little bit. So instead of all of these t as a function of t business, we're just going to write t for this. And we're also going to do the same thing for the derivative. Right, just to simplify things a little bit. Otherwise, it gets a little convoluted. Right, so whenever you see t, this is what we mean. And whenever you see t prime, this is what we mean. We mean t is, it's a function. It's a vector valued function. Okay, so here's what we got. So because, all right, we'll start this off like this. So because t, we know where we got that, right? That was the derivative of r divided by the norm of the derivative of r. Okay, we know that that's equal to the velocity divided by its norm. Okay, so because of this, it follows that, well, just doing a little bit of algebra here, we can see then that velocity is equal to the norm of velocity times t. Okay. So that's kind of our starting point. Now we're just going to differentiate both sides with respect to t. Okay, differentiating both sides with respect to t gets us what? Well, let's write it out here. Gets us this: d dt of velocity is equal to d dt of the norm of velocity times t. Okay, so it gets us that. And the derivative of velocity is acceleration. And what's this derivative here? How are we going to deal with this? Well, let's see here. This is going to be, well, okay, I want to write this. This is the derivative, but I'm also going to write v prime, okay? And then we need to differentiate this thing here, right? So this is going to be kind of a product rule kind of thing, right? So this is a function of t. This is a vector valued function. And so what we're going to do is we're going to write it like this: dt, and then it's going to be the norm of v times just t plus the norm of v times t prime. Right, we can differentiate t. Okay, so I take this derivative times t plus v times the derivative of t. Okay, and so then that is going to be equal to, okay, again, just kind of hanging on to this piece. And this will be the norm of v, and we're going to do a little algebra trick here. And we're going to multiply and divide by the norm of t prime. All right, we can do that. I haven't changed anything. So that's equal to, again, just kind of hanging on to this. Okay, now what are we going to do here? Well, so t prime divided by the norm of t prime, that's the normal vector, right? And so this is, we can write it like this. This will be the norm of t prime times the normal vector. Okay, right, so this one here and this one here became the normal vector, and then this one here we just kind of leave behind. Okay, what next? So, I mean, are we done? We kind of are done already, actually. I mean, these are not the prettiest constants in the world, but this here and this here, these are constants. Right, well, they're functions of t. They're real valued functions of t. The actual vector valued function is here and here. And basically, this is what we're going to call a of t. And this here is what we're going to call a of n. And we'll talk about what that means in a moment, but you can kind of think of them as constants. Okay, so what we've said is that acceleration is equal to this, right? And so obviously, if we write it like this, a is clearly a linear combination of t and n. Okay, and given that, and therefore must lie in the plane determined by these two vectors. Okay, which is what we meant to prove, right? That's what we meant to prove. Okay, and so that's basically another way of saying that is that a can be broken down into these two components, one of which is a scalar multiple of t, and the other is a scalar multiple of n. Okay, so these coefficients here of t and n have specific names. They have specific names, and they're important. They're important in physics in particular. Okay, so the a of t is called the tangential component of acceleration. Right, that's going to be the component of acceleration that tends to act in the direction of velocity or in the direction counter to velocity. Okay, and then a of n, that's of course going to be called the normal component of acceleration. This is going to be the piece that doesn't impact the magnitude of velocity. It's certainly going to influence the direction that velocity is taking, but it's not going to impact the magnitude of the velocity. Okay, now these can be calculated in a more convenient way than than kind of going through this exercise. These can be calculated using, okay, so a of t, right, that's going to be equal to the derivative of, as we saw above, that one's straightforward, it's just the derivative of the norm of the velocity vector, which you can get to by taking acceleration and dotting it with the unit tangent vector, which similarly, I mean, I guess the same, equivalently would be the velocity vector dotted with acceleration divided by the norm of velocity. Right? These are all just three ways of kind of writing the same thing. I think if you experiment with one of these or two, any pair of these, you can see that they can be made equivalent to one another. What about the normal component? Well, we saw up above that it is equal to the norm of velocity times the norm of the unit tangent, or the derivative of the unit tangent vector. Okay, and so it's equal to the acceleration vector dotted with the normal principal unit normal vector, and it's also equal to the norm of the cross product of v and a in that order, divided by the norm of v. And yet another way to get to it is to take the norm of the acceleration, square it, subtract off the square of the tangential component, and take the square root. So that's yet another way to get to it. So if you have the tangential component, the normal component can be calculated, using that piece as an input. Okay. All right, let's do an example. Okay, let's do an example. We'll kind of wrap this one up with this example. Let's find the tangential and normal components of acceleration for this curve. So we want to find a of t. Well, it's not a vector. We want to find a of t and a of n for r of t equals 3ti minus tj plus t squared k. Okay. So this is what we're after, right? And so we saw just a moment ago that there are lots of ways to do this. So we'll start by finding, let's find the velocity. Okay, let's also find the norm of the velocity. And let's, while we're at it, find acceleration. Okay, so the velocity, that's going to be the derivative of this, isn't it? So that's just going to be 3i minus j plus 2tk. That's the velocity vector. The norm of the velocity vector is going to be basically square those components, add them up. So 9 plus 1 plus 4t squared. Okay, and so that's going to be what? 10 plus 4t squared, square root of that. Then what's the acceleration? Well, that's the derivative of this further, right? And so that's a constant, that's a constant. So basically it's just 2k. That's the acceleration. So the acceleration's constant in this case. Okay. All right, and so then by the previous theorem, there were several ways to do this, but the way we're going to do it is we're going to identify the tangential component using v dot a divided by the norm of v. We're going to do it this way. Okay, and so that means we've got a dot v and a and divide by the norm here. So that's going to be what? 3 times 0 plus -1 times 0 plus 2t times 2. All divided by this thing here, 10 plus 4t squared. And it looks like we get 4t, 2 times 2 is 4, times t, and then 10 plus 4t squared. Okay, so that's the tangential. That's a of t. All right. Then what about the normal component? Well, one of the ways to find the normal component is to do this, to take the velocity and to cross it with acceleration, and to divide by the norm of velocity, like so. That seems like it might be the best way to do it. Okay, and so we can do this cross product really quickly. So ijk, so the velocity vector goes in first. Velocity is 3, -1, and 2t. And acceleration is 0, 0, 2, isn't it? Okay, and we can pretty quickly do this. It's going to be -2 times I minus 6 times j, and then plus 0 k. Right, so we got -2i minus 6j. That's v cross a. And so then the normal component of acceleration here is going to be this divided by the norm of v. So -2i minus 6j divided by the norm of v, negative 2y minus 6j, divided by 10 plus 4t squared. Okay, and what do we get? We get, oh, sorry, this is not the, I need to take the norm of this still, I apologize. And that's going to be 4 plus 36 square root. So actually, yeah, my apologies, I did this wrong. Okay, don't worry about that part. So this is the norm, right? So we have to take the norm of this. Okay, so the norm is square root of 40. So that means the normal component of acceleration is going to be the square root of 40 divided by this guy here, 10 plus 4t squared. Okay, so it looks like that. Okay, so all together here, then we have a of t, which we found to be equal to 4t over 10 plus 4t squared, and a of n equal to the square root of 40 over 10 plus 4t squared square root. Okay, so that would be the two components of acceleration. Okay, very good. All right, there's probably more to be said on that, but I think we'll leave it there for now. And next time we'll talk about arc length and curvature. We'll kind of wrap up this section on vector-valued functions with arc length and curvature. And then after that, we'll jump into functions of several variables. So we'll kind of shift gears a little bit. Okay. All right, take care, everyone. See you then.